Okay, so let us start with this week's tutorial, which is week number 10. And this week's tutorial problems are mainly based on thermodynamic relations, thermodynamic potentials, and how they all are interconnected to each other. Based on that, most of the problems are given. So like earlier week, I will follow the same thing, that I will first discuss some of the practice problems, that is a different set of assignment from the current assignment, and then after we are finished with that, I will discuss the problems which are there in the current week's assignment, which is given to you for solving. Mostly we'll see that most of the problems will be common with the practice assignment, but some will be new, and those new problems I'll be discussing towards the end of the tutorial. So keep following so that you also get to know what should be the solution for the new questions. Okay, so alright, let us start with question number 1. So it is saying that if U is the internal energy of a gas, obeying this equation with a certain equation is given, you can see, then what is del U del V at T constant equals to. So this is our practice week assignment, right? So right now what we are solving is week 10. Sorry, I'll be in the full page mode so that it is properly visible to you. Practice assignment. So question number 1 is that you have an equation given to relating your P, V and T etc. thermodynamic terms. So this is RT by V minus B e to the power of minus A by RTV. This is your equation, and you have to calculate what is del U del V at T constant. Now here you can first use the first law of thermodynamics, that is du equal to dq minus dw. This you know from the first law of thermodynamics. So dq is the heat exchange, dw is the amount of work done, and du is the change in internal energy. So because you have to take the partial derivative of u with respect to v, so you have to first know what is du here. So you know that dq is known as T times ds. ds is the change in entropy, and dw is simply p dv, right? So then if that is so, you can take a derivative with respect to volume now, so that you have del u del v at T constant, and because T is constant, so this remains as constant, and only partial derivative is on del s. So del s del v at T constant, minus, because it is a derivative on v, so you take dv under the derivative, and you are only left with this p here, right? So now after we have got this we can further follow using this relation you can use, and you can get to know what is your del u del v at T constant. But first here you have to modify some of the terms or re-denote some of the terms, because you see there is a del s del v at T constant term, but in the question, that is the information that is given to you is not anything that is in terms of del s, right? So you cannot get anywhere from this term, so you have to somehow modify or re-identify this term as something that is known to you or something that you can calculate. Simple, right? So for that we have these Maxwell's equations, where we can find out quantities which are related to that, and we can change the notation to some other quantity, right? So one of those Maxwell equation tells you that del s del v at T constant is simply as del p del T at V constant. There are 4 Maxwell's equations. You can just go back and check that this is one of the equations that out of those 4 equations. So this is there, right? So here we will substitute this term here, as this del p del T term, because you have this information about P, right? So you can take a derivative with respect to temperature and calculate what is del p del T, but that is something that you cannot do with del s del v, because you have no information about the entropy directly. So that is what we do, that we have this T times del p del T at V constant minus P, right? So now you have this P. So sorry, how can you calculate? Now first calculate what is this derivative term del p del T at V constant is simply, you have to take a derivative with respect to temperature. So this is R by V minus B e to the power minus A by RTB. So first you take derivative on this temperature term, and then you keep that temperature term constant and take the derivative on the exponential term, which is like minus A by RV e to the power minus A by RTV into, because there was 1 by T, so it will be like minus 1 by T squared, right? So this is just R by V minus B e to the power minus A by RTV, minus and minus making it plus. So this is R and R cancelling out, this making it A by T, this squared, and this T making it only T, V minus B to the power minus A by RTV. Okay. So if this is the case, then you can further follow up from here that this is equal to T times, then you multiply this whole term on this, because that is the value of this term, right? So first term, if we multiply with T, this becomes RT by V minus B e to the power of minus A by RTV, plus the second term, if you multiply with T, this T and the T cancelling out, so this becomes A by V into V minus B e to the power of minus A by RTV. Minus P is basically remaining as minus P. Now if you follow back, what was P values? RT by V minus P to the power minus A by RTV, right? So this is the same value that we have in this term. So this is just R, do not make a mistake that this is the minus sign or something. This is simply as P, what is given as the equation to you. So this P and this minus P cancelling out with each other, and we are only having A by V into V minus B e to the power minus A by RTV. So this is our final answer, and if you check with the options, you will get option number C as our correct answer. So let us go back. This is your practice assignment set of week 10 that we are solving currently. Okay. So our option number is matching with option number C. So this is the correct answer. Now question number 2 is that find the amount of heat transferred when the pressure on 1 mole of mercury at 0 degree centigrade is increased isothermally and reversibly from 0 to 1000 atmosphere. Given the volume of 1 mole is 14.7 cc and volume expansivity is also given, we have to calculate the heat transferred. Okay. And the process is said to be isothermal and reversible. Okay, let's go back and solve this again. That this is question number 2 you have, where you have this idea that you have to find out what is the heat in this case, and your pressure is increasing from 0 to 1000 atmosphere, right? So the change in pressure dP will be like 1000 minus 0 equal to 1000 atmosphere, and if you have to convert it into SI unit, that is Newton per meter square, that is multiply by 1.013 into 10 to the power 5 Newton per meter square. This is your dP value, right? Now you can consider here that your temperature and pressure are the independent variables, because that is mentioned in the question that temperature is remaining constant throughout the process. Okay, because temperature is constant because it is an isothermal process as per the question, and the pressure is increasing from 0 to 1000, but they are like independent variables and you have those terms as a known terms. So you can consider your entropy to be a function of T and P both, right? So this you can say that ds equal to del S del T at P constant dt plus del S del P at D constant dP. Now you have to know what is TDS, because TDS is the formula for dq. So TDS is simply multiply by T del S del T at P constant dt plus T del S del P at T constant dP. Now one thing you know from thermodynamic quantity idea that your Cp is the specific heat at constant pressure that has a generic formula as T del S del T at constant pressure P. And similarly Cv will also have a formula like T del S del T at constant volume V. Okay, so these are known to us already. So here you can see there is a term T del S del T at P constant. So this you can replace by Cp dt. And why are we replacing it? Because you have the simplified formula that you can utilize here, that this formula or relation giving you Cp dt plus then T times del S del P at T constant dP, right? So here also you can again use a Maxwell's equation to convert it into some other partial derivative form, which will be giving you that del S, one of the Maxwell's equation, del S del P at T constant equal to del V del T at P constant with a minus sign. So for this chapter you have to know the Maxwell's equation or remember the Maxwell's equation very well, because then only you can find out that which equation or which relation will be useful where, and you can directly, in a very straightforward manner, you can directly use that and get to your answer very fast. So you can find out how these Maxwell's equations are derived, and finally for quick implementation maybe it will be better for to remember. If you multiple times use it, you will eventually remember what are the basic variables and signs, etc. So then you can at least understand that okay, these are the variables to us given and these are the variables we want to convert this partial derivative into, and so this Maxwell's equation is there to allow us to do that. So this is one of the useful tricks for this kind of problems, because Maxwell's equation you'll be seeing that we'll be using a lot of times to just redefine some of the terms so that it is easier for our calculation, right? So here also del S del P at T constant we have to redefine or by Maxwell's relation, that this is minus sign, so we keep the minus sign here. So this is del V del T at P constant dP. So you have TdS equal to, now you know that this is dq. Okay, so dq equal to just Cp dt minus T del V del T at P constant dP. Now you have another term in the question, that there is one term called volume expansivity. So alpha is the coefficient for volume expansivity, standardly used like that. And alpha is written like 1 by V del V del T at P constant. So volume expansivity is nothing but the rate of change in volume with change in temperature at a constant pressure with respect to the initial volumes. Like here the initial actual volume is V, so the change in volume is dV, right, let's say. So how much is for the temperature change of dt, so how much is the rate of change in volume with the change in temperature, so that is just del V del T, and this is happening at constant pressure, so P is constant. And with respect to the initial volume, if you want to take the ratio, so then it is just 1 by V del V del T at P constant. So from here you get that your del V del T at P constant is just alpha times V. Alpha is the volume expansivity. So that you replace here, that this is T times alpha V dP. Okay, right. So if that is the case, then now let us put different terms together so that we can finally calculate what is dq. Now first of all, it is mentioned in the question that the process is an isothermal process, so dt is equal to 0 obviously, and the first term becomes 0. So you are only left with this term, and it is mentioned in the question that T is equal to 0 degree centigrade, which is basically 273 Kelvin. Alpha is mentioned as 1.78 into 10 to the power minus 6. It was some SI unit, I think. Let us go back and check. So alpha is okay, not 1.78, this is 178 10 to the power minus 6 per degree centigrade, and volume is 14.7 cc. So this is alpha value 178 10 to the power minus 6 per degree centigrade, and What is the other value? That is the volume is 14 cc, or if you have to convert it into SI, so it is 14.7 centimeter cube, and you know that 1 centimeter is equal to 10 to the power minus 2 meter. So this is 14.7 to 10 to the power minus 2 whole cube meter cube. So this is 14.7 into 10 to the power of minus 6 meter cube. So your dq equal to just minus T is 273 Kelvin. This term I am now putting it all together, into alpha is 178 into 10 to the power of minus 6, into V is 14.7 into 10 to the power of minus 6, into dP is your 1000 atmosphere, which is 1000 into 1.013 into 10 to the power 5 Newton per meter square. So by multiplying all these terms, you will be getting a value of dq, which you can use your calculator to calculate. This is minus 72.36 joule. Minus 72.36 joule. This is your answer of how much is the heat that is needed in the process, and you can match that. This will be your option number D. So let us check. Option number 2, question number 2 is, this is what we have got. So option number D, this is the correct answer. Now question number 3 is about that you have the pressure on a block of copper weighing 1 kg is increased reversibly to 100 atmosphere at 15 degree centigrade. Then find the value of Cp minus Cv for the process. Okay, and given the volume expansivity, again alpha is given, and Kt is basically isothermal compressibility. So these are standard terms, so they have not mentioned explicitly what term is this, but you can understand because they are standard terms. Like K suffix T means it is the isothermal compressibility. Okay, so temperature constant and how much it can compress, that measure is isothermal compressibility, and volume is also given. And because volume unit, you can see that this is meter cube per kg, so generally volume only will be just meter cube, but because there is a meter cube per kg, so this tells you that the mass has to be taken as 1 kg, which is already mentioned in the question, right? So 1 kg and the volume is at some meter cube. So this is just like a density unit, because meter cube per kg makes it a density unit, but for the sake of it, we can know that okay, 1 kg is the mass of the body or the block, and its volume, that is the 1 kg is occupying, is this volume. So this is just a volume only expressed like that, and you have to calculate what is Cp minus Cv. Okay, so again you have to use some of the thermodynamic relations known to you. So you start with question number 3 is that you have alpha, Kt and volume. These are your known things in the question, and you have to calculate what is Cp minus Cv. Okay, so first of all, define some of these terms separately. Like alpha is equal to, as I already mentioned, that this is del V del T at P constant. Kt is isothermal compressibility. This is just like 1 by V, there will be a minus sign, and this will be with respect to pressure, so del V del P, and at constant temperature. So alpha and Kt are somewhat like change in volume only, but alpha is for when the volume is changing with temperature dt and pressure is constant, and the second case Kt is when the volume, what do I say, volume is being changed with respect to pressure. Now the temperature is constant, so they are kind of related, but because there is a Kt, the Kt value has a minus sign, because volume and pressure are inversely proportional to each other. So like if you increase your pressure, volume will decrease, and vice versa. So that is why you have a minus sign at the front, and otherwise it is just a change in volume with respect to change in pressure at a constant temperature, right? So here you have del V del P at T constant is equal to minus Kt V, and del V del T at P constant is equal to just alpha V. Okay, so once you have this, now you can take your entropy to be a function of temperature and volume. Just like for the last question we did this as T and P. So this anything is possible, just you have to understand that what variables will be useful to you in which problem. So like in this case volume will be much more useful volume variable, so you take a function of T and V. Okay, so then ds is simply del S del T and V constant dt plus del S del V at T constant dV. Now you have um, so now if you take what is del S del T at P constant, so you are basically taking a derivative with respect to temperature at constant pressure on both sides of the equation. So del S del T at P constant is equal to just del S del T at V constant into this is becoming 1 plus okay. So after that you just multiply this as T del S del T at P constant. You take this term to the other side, so this is also because both sides are multiplied by T, so this is minus T del S del T at V constant is equal to, this is a plus sign, this term with multiplied by T, so T del S del V at T constant so you know this is the known formula for Cp and this is the known formula for Cv. So simply just Cp minus Cv is equal to T. Now just watch carefully that you have the left hand side already presented to you, that you wanted to calculate Cp minus Cv. So left hand term, left hand side term is exactly like that, Cp minus Cv. But on the right hand side, out of the known equation, known terms or elements that you can have, there is del S del V at T constant, del V del T at P constant. Now if you look at some of the known quantities given to us in the question is alpha and Kt. Okay, so this alpha has this del V del T at P constant term directly in it. So like if you can replace this del V del T at P constant by alpha V here. Okay. But this del S del V at T constant is not matching with the relation that is given in Kt. So for that you have to again use Maxwell's equation and you have to convert this into a form suitable that so that you can replace it in terms of Kt. So this is Maxwell's relation again, that del S del V T constant is equal to del S del V at T constant equal to del P del T at V constant. This is T T del P del T at V constant to del V del T at P constant. Now you can replace some of the terms like what are those? So like so until this point we have obtained up to this part. If you still see there is this term which is not exactly matching with the expression that is given to us in partial derivative, so to further simplify we can actually take use of something else. Like we consider that we know so if that is the case, then you have that these quantities are all related to each other by this kind of a equation. So from that you can get to know that del P del V at T constant to del V del T at P constant. Del V del T del T del P at V constant equal to 0. So from here you can say that your del P del T at V constant, which is this term, and this is the inverse when you are taking it to the other side. So this is equal to minus del P del V at T constant So this is the thing that we are getting, that Cp minus Cv is equal to del P del T, sorry, this thing, and where this term we know from the equation with alpha, but for the first term we have to use a thermodynamic variable relation where del P del T at V constant is equal to minus del P del T and minus minus n. Okay, so if that is the case, then you can further use this equation like, just 1 second. Okay, so while we're discussing, let us continue from there. We are trying to calculate what is Cp minus Cv using different thermodynamic relations, and we got up to this point easily. And after that we have to change some other sort of variables. So for that, because we have to express the final form in terms of alpha and kt and maybe volume, all the known terms. And so basically this is sorted because this has relation to alpha, but this term we have to remodify. So because of that we can change, like we can use this relation that because p, v and t all are thermodynamic variables, so they can have a relation like this f of p comma v comma t is equal to 0, and then because of that they can have a partial differentiation relation like that each of the variables we are taking, and we're taking it showing a partial derivative in a particular order like this, and this is equal to 0. So from here we can get that your del p del t, that is this term's inverse. So if you take so this term is equal to not 0, sorry, this term is equal to not 0, this is equal to, then will be minus 1. So this is equal to minus 1. So if you take this term to the other side, and 1 by that term will be del P del T at V constant, and the other part will be just minus of del P del V at T constant into del V del T at V constant. So then Cp minus Cv will be like T times this del P del T, you modify, there is a minus sign, so this is del P del V at T constant into, again you are getting a del V del T at P constant, there was already a del V del T, so that will be a square term, so del V del T at P constant whole squared, right? Now you have this information about Kt, which is the isothermal compressibility, that your del V del P at T constant is equal to minus Kt times V, right? So from here you can also get what is your del P del V at T constant, just the inverse of that. So this is just minus 1 by KTV. So that is what we write here, that this is equal to minus T into del P del V. This term is just minus 1 by KT times V. To this whole square term is just alpha into V, that whole square. So this is alpha squared V squared. So this minus and minus is cancelling out. So this is just Cp minus Cv we are getting as TV. So this V and V square making it V. So TV alpha square by KT. Right. So now you have all the known terms on the right hand side. So just substitute those terms, like you have 15 degrees centigrade as your temperature. So that is 15 plus 273, which is 288 Kelvin. Right. And now you have all the other terms also known. So that is 288 into volume was given as I think 0.000114 in SI unit. And then you have alpha value. Alpha was given as the volume expansivity, alpha at 5 into 10 to the power minus 5, that whole square, divided by KT is simply, it was also given in the question as 8.6 into 10 to the power of minus 12. So what we will get is just 9.54. Now just take care that here you will be getting the unit as joule per kg Kelvin, because all of the other terms that you started with were in SI unit, so it is joule per kg Kelvin. But in the question they are asking us in joule per mole Kelvin unit. That is the option that is given in the question. So this is also a correct answer, but this is not in the given unit that they are demanding in the question. Also correct. But to satisfy the need of the question that okay, the unit you have to modify, so in joule per mole Kelvin unit as per the given options, you have to further calculate that, because they were giving us the element was copper, that was mentioned in the question. So copper, you have to know what is copper's molar weight. So copper's molar weight is just 1 mole is equal to 63.5 gram. Okay, so this is copper's molar weight. That means your 1 kg will be like 1 by 63.5 into 10 to the power of minus 3 mole. Now just multiply, now let's convert it here, that 9.54. so this was per kg. So if you convert per kg into per mole, so that is, this is joule per Kelvin, and 1 by kg is making you do or put this term as 10 to the power minus 3 mole, right? So this you have to multiply 9.54 into 63.5 into 10 to the power of minus 3 joule per mole Kelvin, which answer will be like 0.61 to joule per mole Kelvin. This is the answer that will be matching with the options that is given. So let us go back and check. So this is question number 3 solving. So 0.61 is in the option number A. So this is the correct answer. Now question number 4. Be very attentive from this point, because from question number 4 the rest of the questions of this practice set are exactly common with the questions that are given in the current week's assignment problems. Okay, so these are all common. So by solving this, we will be already solving some parts or majority of the parts of the current week's assignment. So let us get started. So the expression del P at T constant, del P at S constant, and del S del T at P constant, this product is equivalent to what expression that you have to know, and the options are given in those 4 options. You can see they are all simplified. So basically you have to manipulate the thermodynamic variables or tune them in such a way using Maxwell's relation mostly, that they take the form of the simplified one of those answers. So we can take our question number 4. So question number 4, you have del P del V at T constant, del T del P at S constant to del S del T at P constant. So this we start with. Then you can change some of the terms. So Maxwell's relation you have to use. There you have del V del S at P constant is equal to del T del P at S constant. So first we aim to change our this term, second term, which has this constant term as entropy. So that is exactly same as this term, so we can convert it using that. So first let us do that, and remaining terms will be same. So del P del V at T constant is giving you del V del S at P constant to del S del T at P constant. Now these two terms both are at constant P, and these two partial derivatives, they will be recombining together to give you simply del V del T at P constant, right? Now you can change again this term with some term with the Maxwell's equation, so that you can finally get a simplified term, because To simplify the terms, you have to take the terms constant term to be same, just like you had both constant pressure, so then only we could actually combine these two terms, right? Similarly here the constant terms are different, one is temperature and other is pressure, so then you cannot combine them to give it a simplified form. So you have to change this pressure into some simplified into some variable at constant partial derivative at constant temperature, so that both of the first and second term can recombine to give you a single term. So again you have to use the Maxwell's relation. There has to be something that can match your need, that your P at constant variable you have to shift to T at constant variable. So there is exactly one relation, that del V del T at P constant is equal to minus del S del P at T constant. So this is just minus del P del V T constant into del S del P T constant. So this again you see that T is constant and dP, this del P term is actually recombining and cancelling out to give you a single term which is minus del S del V at T constant. Okay. So this is your final answer. This is your option number D. So you can match your answer, that we are getting the answer as option number D. So the correct answer is minus del S del V T constant, option D. Then question number 5 is that for a homogeneous ideal gas, find out the ratio of the adiabatic elasticity. ES, adiabatic means you have taken the entropy as constant, that is S is constant, because dq equal to 0 is adiabatic, q is constant, and dq equal to just TdS, right? So if dq equal to 0, then TdS will be also 0 and temperature cannot be 0. So ds is 0. That means S is constant. So adiabatic is basically an isentropic process in other terms. So let me write that down, that adiabatic means dq equal to 0, that is T times ds equal to 0. But temperature is finite in the process, so only ds is 0 is making the term 0, or S is equal to constant. So adiabatic also means that it is an isentropic process, or entropy is constant in the process. So when you are talking about the adiabatic elasticity, so generally elasticity term is expressed like how much the pressure is changing with, or how much the rate of change in pressure with respect to the volume, and you have a standard form like this. This is basically the inverse of the isothermal the compressibility term. So inverse of compressibility is basically your elasticity. Only here it is adiabatic, so it is at constant S. But the second term is exactly similar because it is isothermal elasticity. This is exactly the inverse of KT because this is just at constant temperature. So let me write this down as well. So elasticity is, compressibility is inverse. Okay, so just like ET is equal to just 1 by KT. How? Because KT was your just minus 1 by V del V del P with respect to P at T constant. So your ET will be just that inverse. So this is minus V del P del V at T constant. Right, so that is what given here. Only when you have to take again the adiabatic elasticity, then just with instead of S, instead of T you just write S. So this is minus V del P del V at S constant. Right, so now you have all the terms Cp, Cv, etc., and you have this relation. So just now calculate what is the thing that is asked in the question. So question number 5 is that you have to take a ratio of Es by Et. So the already given terms are known to you, that it is del V at S constant, and this is minus V del V at T constant. So this minus V and minus V cancelling out, so you are left with simply del V at S constant divided by del V at T constant. Now you have to remodify some of the variables. So how to do that? You can simply use a partial derivative. This single term, out of this you can make two terms, like you can take one extra del T term on both sides. You can multiply and divide in the partial derivative. So this will be like del P del T, but the constant terms should not change. Whatever you do in the partial derivative, the constant term, which is entropy in this case, should remain just that. So keeping that intact, so del P del T at S constant into del T del V at S constant is equal to just, now you have temperature as the intact term. So this is just del P del S. Now you have S taken as a partial derivative variable and T is constant, and same S is multiplied here also to readjust. So del S del V at T constant, right? Now you have to use some of the Maxwell's equations to convert some of the known variables. So Maxwell's relations. These are del T del P at S constant is equal to del V del S at P constant. So let me write down all the four Maxwell's equation here so that we can choose whatever is needed to us. Okay, so just follow the Maxwell's equation I am writing are correct or not in terms of variables and signs, etc. So these are the equations. Okay. So then you can change your what was that? Yeah, del S del V at P constant was there. So okay. So let us now modify some of those terms. First we'll use this del P del T. Okay, so del P del T at is constant. So this is this term's inverse, and del T del V at is constant is exactly this term. Write down that. So del P del T at is constant is just the inverse of that. So this is del S del V, the first equation I am using. Now the second term, to convert it, we use the second equation. So this is minus del P del S V constant. So from S and T as constant variables, we are changing all to P and V constant variables. You will see why, because in the end we'll be using terms like that. And again, for the lower terms, which are del P del S at T constant is your this term's inverse, and del S del V at T constant is the last term directly. So for the third, for this part we use the third equation's inverse. So this is just minus del T del V at P constant, and for last equation we directly use this last term. So this is del P del T at V constant. So this minus and this minus is cancelling out. So what you have is del S del V at P constant. Okay, and you have del V del T at P constant. So basically we separate out some of the terms now, because both these two terms are of the same constant variable P, so we take them together. We take this as an inverse and put from the denominator to numerator. Okay, and similarly these two terms are also at constant volume, so those two we compile together. So this is del P del S at V constant, del T del P at V constant. Okay, so these are the two terms. Now what you have, this del V is basically common and at constant P, so you merge them together, and this is del S del T at P constant. Similarly, you have del P common, you merge them together and you have del T by del S at V constant. Now these terms start look somewhat familiar, because they both have del S del T at constant P, and the second term is just the inverse of del S del T at constant V. And you know what they are related to. They are related to a specific heat. Like you have now, once I arrange this will be much clearer. So this is del S del T at V constant. Now just multiply a T on both terms, because T on both terms, numerator and denominator, so they will cancel out eventually. And this, you know that this is a ratio of Cp by Cv, because Cp is the T times del S del T at V constant, constant pressure heat capacity, and Cv is the T times del S del T at V constant, constant volume heat capacity. And this is just your specific heat ratio or gamma. And in the question it is given, the values are given to you of Cp and C. They are of the same unit, so I will not write down or convert anything in the units as such. This is just directly Cp by Cv is 50 by 42, which will give you 1.19. So this is your answer. This will match your option number A. So let us go back and check. Okay, option number A is this answer. So this is correct. Now question number 6 is, for the thermodynamic system, the expression T del S del T at P constant minus T del S del T at V constant is always equals to what? So this again you have to now place some adjustment indications and get to the answer. So now that pattern is somewhat familiar to you, you just have to know the relations, what term you need to convert it into, what will be more convenient, and based on that you have to go on. So in the question it is given T del S del T at P constant minus T del S del T at V constant. So you'll see that this is simply the relation of Cp minus Cv. Okay, Cp minus Cv, that is what you need to calculate from here. And if you remember, this is already solved by us for a question previously. So Cp minus Cv is already solved by us to some extent. So we can go back and check that whether that is correctly done or not. So Cp minus Cv is given like a product term before here. So this is something that you have identified or calculated before for the purpose of getting this in terms of these terms. So here Cp minus Cv, we can follow the solution how we started with, and you got to this part, right? Cp minus Cv is exactly this term that is given to you in the question, and you identify it as T del P del T at V constant and del V del T at P constant. So that is the exact answer we'll be needing here. So you solve this again because it's just the same calculation. So the answer is only I am writing del V del T at V constant and del V del T at P constant. So this is your final answer, and let us see whether it matches with any of the options. So this is our option number D, which is the correct option as well. Remember that this is also common end week's assignment. Okay, so from question onwards, all the questions here are is common with current week 10 problem set. So from 4 to 10, these problems are all common with the current week's assignment. So all I am doing is commonly done and new questions. Now question number 7 is, if the equation of state is given by some V related to T and P etc. variables where B is a constant, then which of the following relation is true? Okay, so question number 7 it is. So 7 is P is equal to RT by P minus B by T square, right? Now from here we'll use some Maxwell's relation, and the thing you have to finally do is that what is your just go back, what was the question? Yeah, so which of the following relation is true? What was in options were given in terms of what is del Cp by del T, del Cp at constant temperature. So that is what you need to calculate from this question. And so we have del Cp by del P at constant temperature is what? This is what you need to calculate. So here you have some Maxwell's relation that you need to use. First relation that we need here is del S del P at T constant is minus del V del T at P constant. So del T of del S del P at T constant and at constant pressure is equal to minus, so you take a partial derivative with respect to temperature on both sides at constant pressures. So the second term is simple, this is just minus second order derivative with respect to temperature at constant pressure. Now you have because there is a, you can change or swap the variables in the partial derivative like this manner, like from temperature derivative you can change into pressure derivative. So this becomes del P, and this inside derivative now is changed to temperature. So this is del P of del S del T, and at constant temperature now becomes constant pressure here, and the final constant pressure becomes constant temperature here. So this is just equal to minus del 2V by del T2 at constant pressure. And why are we able to do that? Because entropy S is a state variable. So it depends on the particular, like temperature, pressure, etc. on the particular state. So the order of the partial differential does not change anything. So because of that, either you take first derivative with respect to P at constant temperature and then take a derivative with respect to T at constant pressure. This will be same as first taking the derivative with respect to T at constant P, and then on top of that you take a derivative with respect to P at constant P. So that's change the order of the partial differentiation. Order of partial differentiation short P full stop D changed or swapped. So now once you have that, so now you have Cp you know as T del S del T at P constant. Now then what is del Cp by del P at T constant? This is just T del P del S del T at P constant at T constant. So now you have one by T del Cp del P at T constant. So this total, this T comes this side on the left hand side. So this is just del P of del S del T at P constant at T constant. Now this term you already know that this is your minus del 2V del T2 at P constant. So you can substitute that here, that this is minus del 2V del T2 at P constant. So what you have is here del Cp by del P at T constant is simply minus T times del 2V by del T2 at constant P. Okay, so this is your final thing. Now you know what is your expression of V, right, from here. So you can take a derivative with respect to temperature double times and you can get what is the thing that is needed on the right hand side. So first take a single derivative del V del T at constant pressure. So this is R by P 2B by TQ. And the second type derivative is del 2V by del T2 at P constant. This is just 0 minus 6B by T to the power of 4. So just that is minus T minus 6B by T to the power 4, which is like plus 6B by TQ. So you get that del Cp del P at T temp constant is proportional to T to the power minus 3. This is your final answer and this is your option number D. Let us match the answer. because option number D is not correctly visible here, but this is the option that is t to the power minus t was given in the second last option. So option number D is the correct option. Now question number 8, again this is also common with the current set of assignment. So it is saying that if the volume expansivity is given as alpha is equal to this thing, you know already the volume expansivity formula, then find the ratio of adiabatic to isobaric volume expansivity alpha S by alpha P. So we had a similar questions before where we had the isothermal and adiabatic elasticity ratio. Now you have the volume expansivity ratio at constant adiabatic means at constant entropy S, and then isobaric is constant pressure or P. So alpha S by alpha P ratio you have to calculate, and in terms of the known terms are Cp and Cv. Okay, so these are the known terms, you have to modify them into, to reconvert them into to get to the final answer. So start with option number 8, question number 8. So question number 8 is saying that alpha S by alpha P is equal to, so basically you know that alpha formula, so the V and V cancels out on both top and bottom, so you are only left with this. Okay, so this was I think 1 by V, 1 by V, so these are cancelling out, so these are the main terms that are left. Now you can use the Maxwell's relation, right? So Maxwell's relation are what? So you had a relation that your del V del T at P constant minus sign equal to del S del P at T constant. So first term we replace it like that. So this is minus del S del P at this was at A, sorry, I made a mistake. This was not the relation because there is a constant entropy term here. So del V del T at S constant is basically, the formula is del T del V at S constant is equal to minus del P del S at V constant. So this is the reverse of that. So we are getting this is the reverse of that. So minus del S del P at V constant divided by, you keep your del V del T at P constant as intact. Now you can again modify the numerator. So this is now take and adjust a partial derivative extra with respect to t. So this is del S del T at V constant into simply del T del P at V constant. Just adjusting and rearranging the terms like that. So now you have, what you have is T del S del T at V constant. So multiply a T on the numerator on with this term divided by your minus sign is there. So again a T will be there because to adjust this numerator T. So there will be another T in the denominator. This is T del V del T at P constant to del P del T at V constant. So the numerator term is CV, C at constant volume, V del S del T V constant, divided by, if you remember that this is your minus Cp minus Cv term, because just in the last question we in two questions we had this relation coming, that Cp minus Cv can also be written as T del P del T at P constant and del V del T at P constant. So that is the thing that we have replaced here, only with the minus sign. So this will be like minus Cv by Cv minus Cp, right? So Cv and Cp values are given to you in the question, so you put those values. Cv is 42, all have same unit, so you don't bother about the unit while taking the ratio. So this is 42 by 42 minus 50, which is like 42 by minus 8, which is like minus 5.25. So this is your answer. Option number B will be the correct option to this. So let us check. Yeah, so you are getting minus 5.25, which is option number B. So correct answer. Then question number 9 is, if G and Fr gives free energy and Helmholtz free energy respectively, with the following is true. Okay. So So here the idea of thermodynamic potential comes into use. Okay, so question number 9 we start to solve. G is, you know that this is equal to U minus Ts plus Pv. This is the thermodynamic potential relations of Gibbs potential, and Helmholtz potential F is just U minus Ts. So G is just F plus Pv, another relation, right? So from here F is equal to G minus Pv. And I have to finally get F, because in the options are given F equal to what? So if F is equal to G minus PV, then you put G minus V. You can change like in terms of a partial derivative on G. So first for that you have to know the relation that dG is equal to minus SDT plus VdP. So there are four relations that will be useful to you to always remember. So I'll write them down together here, like du equal to TdS minus PdV. Then enthalpy dA is equal to TdS plus VdP. Then dF, the Helmholtz free energy change, is equal to minus SdT minus PdV, and then dG is equal to minus SdT plus VdP. So this is the dG relation where the variables that are changing are T and P, right? So you can take derivative with respect to that, and if you have to take what is the volume term here, this is just del G del P at T constant, right? So you can replace the volume term here like that. This is del G del P at T constant. So this you can modify it like that. This is how you can express this term in a simplified compact manner. So for that, your del P of G by P at T constant, first let us calculate that. So first of all, this is del P. The first term remains 1, so we take the derivative on the G term first, okay, then plus G minus 1 by P squared, okay, second term. So this is, if you take 1 by P squared minus 1 by P squared as common, so this is G, the second term has minus now, this is minus P del G del P T constant. This is your del P of G by P at T constant. Now you can further solve it by, if you take del of 1 by P of G by PT, okay, because for that then you have this del P, you can again do things like this, that your if you, let's say, separately calculate one to calculate what is your del of 1 by P. So simply it will be like del P of del P del of 1 by P. So this is 1 by del of 1 by P by del P. Del P is a partial derivative on whatever variable you are taking that on. So this is 1 by P, del P is minus 1 by P squared del P on whatever variable you are taking the derivative on. So this is just minus P squared del P of that. So from there you know that this is minus P squared del P of this thing is just, so if this is the case, then you take this P squared to this term, okay. So this is minus P squared del P of G by P at T constant. This is equal to this term, G minus this whole thing. And this is the term, if you remember, this is the term on F, okay. So this is the F term, what you got here. So if you take your P square minus P square to up here, so this is just equal to F then. So just now we did that minus del P square del P is something like del of 1 by P. So del of 1 by P of G by P at T constant is equal to F. Or you can say F is equal to del of G by P by del of 1 by P at T constant. This is a simplified compact form, and this will be matching your option number B. So our option number B is this term. So we have got the correct answer. Now the final question is on what is the change in Gibbs free energy for the following reaction for 1 mole of glucose. So you can see here that glucose is the first term, C6H12O6. There is a reaction given for glucose plus oxygen of 6 moles. Glucose is 1 mole, oxygen is 6 moles, and it is giving you 6 moles of carbon dioxide gas and 6 moles of H2O, which is also in gaseous form. So you know how to calculate this Gibbs free energy from a reaction. Is basically change in Gibbs free energies, total Gibbs free energy from the product of the reaction, final product, minus the total Gibbs free energy from the reactant in the equation. The products the elements which react initially to get to the product. So final minus initial, final product minus initial reactant. In this case, your final products are two products, CO2 and H2O, both in gaseous forms, both are of 6 moles. And the initial reactants were glucose itself, C6H12O6, which is 1 mole, and 6 mole of oxygen. Now this Gibbs free energy is coming when an element is not in its stable phase or its standard phase. Then for the formation of that element, you have to have some finite Gibbs free energy. So like for glucose and carbon dioxide and oxygen and H2O, the Gibbs free energy is given in the question directly in kg per kilojoule per mole unit. But you may wonder that why they have not given any Gibbs free energy for oxygen. So that is because the Gibbs free energy for oxygen is 0, because the formation energy needed for oxygen is 0, because oxygen in gaseous form is already in its most stable state. So there is no energy expense for it to form as a oxygen gas. So that is already the most stable standard state. So because of that, the formation energy or formation Gibbs free energy of oxygen is 0. So G of oxygen will be 0 always. You can find it this internet and research in details why this is so, but this is the answer, that always this part will be 0. So remaining terms have non-zero terms, so let us solve that. So first of all, 6 into CO2 Gibbs free energy, which is minus 394.4, plus 6 into the H2 Gibbs free energy is minus 228.6. This is one thing. Minus for the reactant part, glucose is 1 mole, this is minus 910, and plus 6 is oxygen, into 0 is the change in Gibbs free energy. So finally, by calculating it, you can find out this is 2828 kilojoule per mole is the change in Gibbs free energy for this process. So this is our option number A, that is the correct option. Again, I will remind you that all the 6 or 7 questions we have solved from question number 4 to 10 are all common with the current week's assignment. So now, once we have finished the practice set of previous week, like for week 10s only, but for the old year's assignment, but now we current year's assignment, we take a look at that. First, like I said, from question number 4 to question number 10, you will see that exactly common. So all we have just now solved. So we are left with 1, 2 and 3, which are new to us. We will solve that. So question number 1 is again del U del V at T constant. You have to calculate in terms of Cp, Cv and beta P. Beta P is the volume expansivity. So instead of alpha, they have now given you the notation as beta P. So let us solve that. So this is the current week 10 problem set. Question number 1. So you know from first law of thermodynamics that you will be very quick on this part, because I'll just giving you hints or maybe the structure of the solution, and you can solve the rest of the part. So du equal to TdS minus TdV, right? So in the question they are asking del U del T at V constant. So simply minus P, and then this you can change by Maxwell's relation to that del S del V at T constant is some Maxwell's relation that you can find out. I have already listed down everything above. So this will be, I'll be directly using that del P del T at V constant. This is using Maxwell's formula or Maxwell's relation. I have changed that. So now once you have that, now you can adjust and multiply one term on both numerator and denominator, and that is del V del T at P constant. So to adjust that, you have to also multiply it or present it in the denominator. So this is the case, minus P. So this term is familiar to you probably up to this point. This is just a simplified form of Cp minus Cv, and divided by the this term is basically your beta P times V, because beta P is the volume expansivity, which is 1 by V del V del T at P constant. So del V del T at P constant is simply beta P times V minus P. So this is the answer you will be getting, Cp minus Cv by beta P V minus P. This is, I think, matching with your option number C here. So we are getting option number C as our correct answer. Now, question number 2 is about ideal gas 1 mole under pressure P has density rho and the molar specific heat at constant volume is Cv. So then the ratio of Cp by Cv is gamma, then the entropy of the gas is what? So let us solve it here only, because then I have to otherwise go to a lot further to actually reach to the solution part. So let us solve it here, the side. Question number 2 is that, first you know that ds equal to entropy change is dq by t, which is like du plus pdv by t, and du you know that this is cv dt by t first term, and pdv is basically, because it is ideal gas, so pv equal to rt for 1 mole of ideal gas. So then p by t is simply r by v, so the second term is r by v dv. Now you have ds equal to this thing, so this is s, you can integrate out, so this is cv ln t plus this is r ln v plus some constant which is the integration constant. Okay, now you can say that t is your pv by r, okay, plus r ln v plus constant. So now disintegrate this ln part. This is cv ln p plus cv ln v minus cv ln r plus r ln. Now here you can replace the volume in density terms. So you know that density rho that is given in the question is mass by volume, but nothing is mentioned about the mass in the question, so you take the mass as 1 kg. So this is for simplification. If you take 1 kg, so simply rho is 1 by v, or v is equal to 1 by rho. So here put, instead of v, put 1 by rho plus constant. Now simply look at it, that cv ln r, where cv is known, r is known from universally known constant. So cv ln r can be a constant term, it is not a variable, so you can readjust it into the constant term, integration constant, and simply deal with the other parts, which is cv ln p plus cv ln 1 by rho plus r ln 1 by rho plus a net constant, which is including this constant and this constant term with r term, which we have obtained later. So this is cv ln p minus cv ln rho, because this 1 by rho is minus ln rho, minus ln again same, minus r ln rho plus constant. This is your s. So now you have cv ln p minus cv ln rho minus r is just cp minus cv. Or you can rather take this cv plus r with together and take ln rho common plus constant. So s is now your cv ln p, cv plus r is cp, cp ln rho plus constant. Now your cp minus cv is equal to r, that you know, and Cp by Cv is equal to gamma, specific heat ratio. So this gamma times Cv minus Cv is equal to R, or Cv into gamma minus 1 equal to R, or Cv is equal to R by gamma minus 1. So this is R is basically then Cv times gamma minus 1. So this is Cv ln P minus Cp is just Cv plus R, so that we just now converted. So Cv plus R is basically Cv plus Cv gamma minus 1. So this is Cv times gamma, because this Cv and this Cv will be cancelling out. So we are finally getting Cv ln P minus Cv gamma ln rho plus constant is equal to S. This is your entropy. So this will match your option number D. You can check. Here we can check directly. Yeah, so this is matching, because here we can further adjust these terms as Cv ln of P, where this has a minus sign and this gamma will come as a power. This is rho to the power gamma plus constant. So this option number D is the correct answer. Sorry, this question. Now question number 3 is the last remaining question. It's saying estimate the change in entropy for a gas obeying the equation of state, this thing, and undergoes isothermal expansion from volume of V0 to 2V0. So let us solve this here again. So question number 3 is that you have isothermal expansion, and they are asking what is the change in entropy. So you know that del S can be written as del S del V at T constant dV if V is the only term that is changing here, as temperature is constant and V is changing from V0 to 2V0. Now if that is the case, then from Maxwell's relation you know that del S del V at T constant is also equal to del P del T at V constant dV from V0 to 2V0. Now the gas equation was given as P plus B V equal to RT. So P equal to RT by V minus B. So del P by del T is equal to just R by V. So this is R by V dV V0 to 2V0. So this is R ln V V0 to 2V0. So this is R ln 2V0 by V0. This is R ln 2 is delta S. This is the final answer. So you can match that the answer is question number A. Okay, so we are done with this fixed problem set, and hopefully this is clear to you. So we'll meet in the next week session.